grow and develop is increasing exponentially because now you're using machines to produce. So as you start to bleed labor away from agriculture, what is that doing to your overall economy? Yeah.
The graphs in comparison are per person or?
No, it's not per person.
Because this one is aggregate total and that one is representing what?
Also aggregate total, but it's the Neoclassical Model,
Oh,
and I'll talk
sorry.
about it in just a second. All right. So what this means is that you can start to bleed workers away from agriculture without significantly decreasing production. What this marginal product graph is doing, it's basically saying, we're going to graph, if I made the same graph for this production function right here, it would start high and then go low when I'm looking at it this way. And I haven't switched the axes. Does that make sense? Because the slope starts high and gets lower and lower. All right? All they did was turn this around to give you this graph here. All right? And you start to wonder, why would they do that? What does that help make clear? All right? I'll take you through that step. The way, and this is kind of tied into microeconomics, so I don't want to get bogged down in this too much, but wages are tied into marginal product. So if we go back to the bakery example, if I can, if I have one worker baking 10 loaves, his marginal product is 10 loaves, that's his wage rate, 10 loaves. If I kick up to 2 workers, and I've got to pay everyone the same, they now make 18 loaves, their marginal product of the second guy is 8, you're starting to decrease the wage rate because the workers are getting less and less productive. So you get to a point where when you talk about supply and demand of the labor force, if you have to pay a certain wage, let's say it's 8 loaves, you're not going to hire anyone beyond that second worker because the third worker is going to make less than 8 loaves. You're going to be paying the worker more than they're making. So what Professor Shinai talked about was that there's some subsistence wage here. And the way I think about that is you don't even need to think in terms of what they're physically getting paid, but it's all the food they can grow just to eat to live. That has certain value. And they're not going to leave that job in agriculture to go work for industry if they're going to get paid less than what they could use that money to buy in terms of subsisting to live. All right? So for the purposes of thinking about industry, they're going to have to pay above that level. So you can think of subsistence as the minimum wage. So even though this labor force isn't making anything per se, you would still have to pay them that wage to get them away because they're just splitting up all the food that's grown. So once you get to this point, that's when you need to start worrying about paying them more. So let's say that this number right here is 250. All right? As industry, I could take and hire 750 workers at the subsistence level. But once I want to go beyond that, I've got to start paying them more. Now, what that's useful for determining is the supply of labor for industry. And that's what this last graph is showing. It's saying that the wage rate that you've got to pay in industry is equal to this graph. And what's unique about that is normally, if you don't think about this subsistence wage, the supply of labor tends to rise, not necessarily in a perfectly straight line, but it'll rise over the length of the graph. What this does is it says you're making a flat line because that's your subsistence wage, and you only need to raise above that once you get to this point above the subsistence wage. So this becomes the supply graph for the supply curve for labor. And we don't know what the demand for that labor is in industry, but if wages are high, demand will be low. If wages are low, the demand for labor will be high. So the demand curve always goes from top left to bottom right. So we don't know exactly where it's going to be, but the point is that as demand for labor increases, the amount that they'll have to pay in wages for a long time won't increase. And so with the labor surplus model, it's saying since you've got this surplus of labor, it makes it easy for the industrial sector to grow under this model. All right? I'm going to come back to this model in a second. I'll take your question right now, but I'll come back to this model in a second. But we'll talk about how this one is different in that respect first.
So, I thought that bottom one was supposed to be in industry.
This one is, you can think of this as the supply curve of labor for industry, and this is the demand curve. These are the D's, and this is the S. So yes, this one is for industry, but it effectively takes the same shape as this one because you've switched the numbers. Now down here, since you're looking at a different industry, the numbers are back to 0 to 1,000 because it's the opposite perspective. So yeah, this one's for industry, this one's for agriculture.
Okay.
All right? Yes?
Would it make sense then to think that the industry will hire workers as long as they earn their marginal product or not?
Yes, exactly. If industry can, if hiring this many workers, their marginal product is still above the subsistence wage, they'll still continue to hire more and more workers. All right.
So is the variable there like LI or
You say
for
LI.
labor in industry or?
Oh, yeah. I'm sorry. Yep. Yes. All right. Now, go ahead.
In the middle graph on the left,
Mm-hmm.
we used to have a dashed line there. Is the space between what was the dashed line and the bottom line, is that a difference between zero income and subsistence income?
Yes, so
Okay.
this would be 0 marginal product of labor in agriculture. All right? The difference is that as you bleed labor away from agriculture, you might start with 1,000, but once you cut it down to 250, now you're getting to a point where if you take labor away, they can no longer work, they can no longer max out agricultural production. Their individual production is increasing and increasing, so that's why this starts to go up.
So is the bottom line, that's not wages, that's production.
Correct. This is marginal product of labor in agriculture, all right? The point is that by switching this, we've identified the supply curve that you would put on a wage scale for industry. That's what this allows us to do. The way we couldn't figure this out except by knowing this. So that's how we get from here to here and figure out what's going on in industry, this whole separate sector of the economy that we're trying to develop. Yes?
Then if the bottom one is for industry, then can you change the quantity labor in
Oh, yeah,
industry?
yeah. Yep.
Okay.
Now, the neoclassical model is different in that it's saying that you are not maxing out production in agriculture. If you add more labor, you'll continue to get more production. That means that the marginal product of labor is never going to be 0. It's never going to be down at the bottom because you're still getting more production out of the workers here. And think of this as 1,000. This is 0.
Can you repeat that part, please? The
Yes.
neoclassical.
All right. If you haven't maxed out agricultural production, it'll increase with more labor. That means if I give you another laborer, you can get more agricultural production. That means that that additional laborer produces something. Their marginal product is bigger than 0. That's why this curve won't hit 0. All right. The distinction here being that you've got so much excess labor in agriculture that if I add another one, they're not going to produce anything more. That's why it hits the bottom axis here. All right. The impact is that here, that will always be rising. So in theory, it gets a little bit harder for industry to develop because as it grows, the wage rate is consistently rising. Because each worker that you pull from agriculture, you got to pay more and more, because agricultural production is decreasing. So in this one, initially, the upside is that developing industry should be a lot easier. In this one, it's not. But there's another conclusion that you have to draw from this as well, and that's the impact of population growth. And that's why I drew in these dotted lines here, which I'll explain. In the first model of labor surplus, if you increase the population, you're not increasing agricultural production at all. And that's, since population is going to increase everywhere effectively, population increase is really disastrous for this model, because as you increase the labor force, you're deflating wages everywhere, all right? The only people that benefit are like the people who, you know, happen to own land or farms. Like, it's going to be a very limited subset of the population, because you're adding people to agriculture, they're not producing anything more. You've got more labor surplus, so that makes it cheaper for industry to bleed people away from agriculture. So population growth in a labor surplus model is basically disastrous. On the other hand, on the neoclassical model, population growth can be accommodated, because since you still have room for additional agriculture, if you were at 1,000 and I take you out to 1,250, you're going to still increase agricultural production. Out here, instead of 1,000, now we're at 1,250. The marginal product will fall, but it still won't be zero. Right? And it'll still have this effect, you know, out here on wages. This would shift over, because we have to shift this now from 1,000 to 1,250. So you can get increased production in the agricultural industry, and you're not necessarily deflating wages across the entire population. So it has two different conclusions about two different issues. The first is about what the impact of the growth of industry will mean for the rest of the economy. In the first one, in labor surplus, industry can grow without a decrease in agricultural production. In the neoclassical, for industry to grow, agricultural production must fall. That doesn't mean that it'll fall, like, it doesn't mean it's not worth developing industry. You just need to understand that there will be a cost there. The second issue is the implication of population growth. In the labor surplus model, population growth is very detrimental. In the neoclassical model, it's not. There's still room for an increase in agricultural production. So if you wanted to try and combine these two models into kind of one hypothetical scenario, I was thinking about China, whereby initially you could argue that they had a labor surplus in agriculture, because there's not that much arable land in China compared to the size of the population. So they were able to bleed labor into industry relatively painlessly. But they recognized initially that the consequences of population growth would be very bad, so they artificially decreased the population growth rate by passing laws that said you could only have one child. Now, as China develops and they start to experience technological advancement, the amount of agriculture that they can produce on a given amount of land provides the opportunity for there to be increased agricultural production, such that now they can shift to a model whereby population growth is not so disastrous, as long as they can increase production and capitalize on extra labor in the agricultural community. So the growth of the population doesn't have these disastrous consequences across the economy. Right? Yes?
Can you just sum up the in labor surplus model, which
Yep.
is the on the left in the middle, industry can grow without agriculture fall. In the meantime, neoclassical model, which is opposite, for industry to grow, agriculture production must fall.
Correct.
Right? That's the opposite. And then the same applies to population growth.
Okay. You were right on the first one as far as industry can grow for a long period without agricultural production falling. It can't grow forever, but it can grow for a long time. You've got a lot of surplus labor.
Okay.
The population implication is different. Adding population in this model depresses wages everywhere because you cannot increase agricultural production.
I'm sorry, depresses what?
Wages,
Wages. Okay.
right?
This is the labor surplus model.
Correct. Because think about it insofar as if that labor is initially assigned to agriculture, they're not producing anything more, but you've got a much bigger workforce for industry, wages get depressed.
And in the neoclassical, it would be what? Once you add a population, what happens?
When you have additional population growth, you can assign part of that labor force to agriculture, which in fact you need to, because since you have more population, you need to feed more people, you need to boost agricultural production. So part of that labor force will go into agriculture. So the effect on wages is mitigated in two pieces, whereby you don't have as many people going into industry, and the wages in agriculture can stay relatively high because production is being increased. So it stays relatively costly for industry to bleed that labor away from agriculture.
Thank you.
All right. That's what I think you need to understand from the two sector models. All right. Now, as far as covering some of the more technical stuff from the income inequality piece, the first one was the size distribution. And it's pretty straightforward, but I heard a question during class, which that was when I put my hand up, but I was concerned I had misheard the question, so I didn't want to jump in. But it was, size distribution is the percentage of wealth held by the top 20% of the population over the percentage of wealth held by the bottom 20%, or the bottom quartile. And I think there was a question to the effect of, but if a lot of that wealth is held by the middle quartile, how does that affect the size distribution? You need to understand, I think the framework is, the top quartile always has the most wealth. If people in another quartile, make a discovery and start earning a lot of money, now they are the top quartile. So the top quartile will always have the greatest percentage of wealth of any of the quartiles. That's why they're the top quartile. Yes?
I'm sorry.
Sure.
What you just said starts at 25%. We're talking about quintiles.
Yeah.
Okay, okay.
Quintiles.
Okay,
Thank you.
no
Thank
problem.
you. All right. So if I list each quintile, this is the first quintile, second, third. So this is top, this is bottom. What has to be the relationship of the percentages in each of these quintiles?
You have to add to 100.
They have to add to 100, all right? So that's number one. When I add them all, they have to add to 100% of the wealth. What else?
They'll be going from smallest to greatest.
All right, good. This quantity, called quantity 1, has to be less or equal. Less than or equal to quantity 2, which is less than or equal to quantity 3, which is less than or equal to quantity 4, which is less than or equal to quantity 5. There's no situation under which this number could ever be larger than this number. Otherwise, quintiles, I keep saying quartiles, those quintiles would switch. 2 would now be the bottom, all right? So if you look at the figures in the book, and I haven't, but it should meet that. So if income was perfectly distributed, then this would be 20%, this would be 20%, this would be 20%, this should be 20%, this should be 20%. And people often look at the top quintile and say, wow, it's 40%. Well, that obviously is a substantial fraction of the wealth compared to their numbers, but your starting point whenever you look at that number has to be that it's going to be greater than 20%. It's the top quintile. All right. So that's size distribution. Any question on that one? Yes?
But if you're second, third, and fourth,
Mm-hmm.
you didn't add up to,
20 by 20.
you know, what if they added up to 64% total?
Okay. If these three added up to 64% total,
Uh-huh. So your top one obviously is going to be somewhere around 30%, and your bottom one's gonna be small.
right?
And then you have a large distribution, but most of your population's well taken care of.
But then one of the quarters in the middle would be bigger than quarter 5, and they would have to be switched.
Well, not necessarily. Under the situation you've described, I could have this be 32%,
Mm-hmm.
and this be 4%, and this could be 10%. This could be 20%. Whoop, no.
It would have to be 20%.
I was thinking
21,
somewhere,
21,
you know, running
22.
the, okay, everyone's about 20% in the middle.
Okay, all right.
It was just
we'll
where I
say
was
20, 21, 23%.
Yeah, so
So that would meet.
that would meet this guidance, but
Yep.
your size distribution is, that doesn't tell the whole story.
No, it doesn't.
4 to 32.
No, it doesn't. It's really looking at the extreme tails and talking about what is the difference at the absolute extreme. It doesn't speak to anything about the distribution within the middle quintiles. All right. So that's a really good observation, but you need to understand any of these descriptions are going to have flaws to them. All right. One of the challenges being just comprehension. The more accurate it gets, the harder it is to understand or calculate. Okay. This is very simple to calculate, but it's also comparatively nondescript. Right. Yes.
Well, I was just going to say, but in a very remote way, it does give some kind of a bearance, some kind of an indication of that relationship, because 2, 3, and 4 are 20, 21, and 22. 5 is only at 34 as opposed to 50, or so it does have some, although it doesn't speak of. I would think then that the ratio does speak of how much is left in the middle, but not necessarily the distribution among the three in the middle.
Yeah, and
Maybe I'm wrong. I'm not a
In this class
mathematician.
today, so.
One of the challenges I think that comes up with this is that as economies grow, the intuition to me is that there are always going to be people that are, not always, there are people that are going to be relatively poor, and as you grow, that's going to tend to increase inequality, but it doesn't speak to the quality of life that people have. So that the example you gave of Bangladesh, where they have relatively equal income distribution, well, yeah, because everyone's poor. So it's a lot easier to achieve income equality when everyone's poor than when you start to get development. Yeah. So that's not a value judgment, but I just say, like, that's where you got to start to consider the value of these metrics. You know, what they're telling you, is it enough to draw the conclusions that people often draw from it? All right. The Headcount Index.
I know.
That's just the number of people below the poverty line over total population. Often abbreviated HI. The Gini coefficient. Personally, I like the Gini coefficient. I think that it accounts, it doesn't tell you everything, but it accounts for a lot of what's going on in terms of income inequality that the other figures don't. So I don't know exactly where the inequalities start to develop, but I got a sense, a better sense of how unequal the situation is. So this is
Are Gini coefficient and the Lorenz curve used interchangeably?
no. They're highly related, but they're not interchangeable. All right. To describe what we've got here, the Lorenz curve is this curve right here. That is the piece that's unique to every country, the curved portion. The straight line at a 45-degree angle is a reference point that will be the same for all countries, because the 45-degree line would describe perfect income distribution. And the way that we work through finding these intuitively is start to say, if I've got 1% of the population, if we've got perfect income distribution, what percent of the total income should that 1% have? 1%, all right? That's their equal share. If I'm looking at 50% of the population, what percent of total income should that half of the population have? 50%, all right? So a lot of people get confused looking at this and somehow thinking that automatically this section is poorer than this section. Not if there was perfect income distribution. If there was, and this straight line described the country, then everyone would have an equal amount of income. The reality is that you never have perfect distribution, so you get some curve. And let's say that we look at the first 10%, the lowest 10% of the wage earners, and they earn 2% of total income. Then I would go up for 10%, go across, and that would be a 2%. If I look at the next 10%, and I find that they make 4% of the total income, this now goes, because this is cumulative, I'm adding the 4% from this 10 to the 2% from this 10, that would be 6%.
Can you repeat the one you added the cumulative part?
Sure. All right. Let me just erase these numbers. All right. I start by looking at the poorest 10% of the population, and I find out that they earn 2% of total income. You follow that piece so far?
Mm-hmm.
All right. What I do then is, let's do it without the graph there yet, and say, I look at the first 10%, and I see they make 2% of the income.
Mm-hmm.
So I go 2%, and I make a dot right there. Then I go to the next 10%. So this 10%, I find that they earn 4% of total income. So I got to add that 4% to the 2% I already have. So that's 6%. I go up there, I make a dot right there. And basically I do that progressively,
But why not?
and that will define the Lorenz curve for that country.
So 10% is 2%. The second 10% wouldn't that be cumulative
4%.
20%?
No.
No.
It's
4%.
20% of the population,
Yeah.
but that 20% together, they make 6% of the income. Because that's the poorest 20% of the population.
But how do you, okay, how do you know that? So the starting assumption is that with 10% making 2, you then can say 20% makes 6?
Okay, so how would we figure this out? The way you could do it in a hypothetical situation, let's say we took the income tax returns for the entire United States, and we lined them up from lowest income to highest income, all right? And I've got 100 tax returns, that's everybody. I would first add up how much those 100 people made. Let's say it's $1 million, all right? Let's keep it simple, let's say it's $100, okay? Those 100 people earned $100. I would go to the first 10 tax returns and see how much those 10 people made. And I would see that I would add up their 10 tax returns and they made $2 between all 10 of them.
Okay.
That gives me my first 2. I'm done with that 10. Now I go to the next 10 tax returns. And I say between all of them, they made $4. So the bottom 20 tax returns made it $6.
Okay, get it.
Oh, okay.
Do you see that?
Yeah.
All right. Then I would go to the next 10 tax returns and I saw that they made $10.
So the bottom 20% would be 6%.
Yes, because it's cumulative.
Okay.
All right. And the way I would see how much that 10% made, I would have to find out the difference here. So I'd go 6% minus 2%. This 10% made 4% of the total income.
And then the third 10% will be in total the bottom 30%.
Exactly. Exactly.
So
you're adding the total population and total income.
So the bottom 30% would do 10%, then the third 10% would do 4% as well.
Exactly. All right, and each one would have to be a little bit more because the graph is going up. It would never look like it would never go up and then down and then up again, because obviously then these people were making more than these. Switch them around, all right? So you're always going to get a curve that's climbing.
Wait, I'm sorry, but can we repeat what happened to 30%?
Okay, so the next 30%.
The next is 10%.
Yeah, I'm sorry.
Right, okay.
The next 10% here, they make 6% of the total income, let's say. So I have to add the 6% they made to the 6% that's already been made.
Okay, so that's arbitrary. You just said 30%
Yeah.
makes 6%, but the point is that it's cumulative to the whole 30% to add all of their.
Exactly.
Okay.
And I did make the numbers arbitrary, except to the extent that they've got to get bigger or be the same each time. So it had to go 2, 4, 6. It couldn't go 2, 4, 2.
They could be the same though? Like 2 sets of 10% could have.
Theoretically.
Okay.
It's never going to happen, but if within that sector income was perfectly distributed, then yeah, they could be the same. It could never be less though. All right? Everyone feel comfortable with the curve and how it's derived? All right, so then the next piece, getting to the Gini coefficient, and don't worry about numbers for figuring this out, just understand where the information would come from. So the way you get the Gini coefficient is you take this area here, and if you had the data, you could figure out these numbers. We're not worried about the numbers. But you take this data here and divide it by the entire area. So you're going to get a percent. Now, don't answer out loud. Just think for a second. if you want equality, do you want your Gini coefficient to be close to 1 or close to 0? Just think about it for a second. Don't say it. Just think about how we get it. What perfect distribution of income would mean. And think about, do we want a Gini coefficient close to 0 or close to 1? In a second.
I'm sorry, could you repeat that?
Sure. Let's say that your goal is to have, you want to emphasize equality. All right. Do you want this country to have a Gini coefficient close to 0 or close to 1? Because it's going to be a fraction, since you're taking this area
0.
right here and dividing it by the total area.
For the equality, I would say 0.
Okay, good. The closer it is to equality, the closer the Gini coefficient will be to 0. Because think about it, if we have something really close to equality, it's going to be very close to that line. So the area A is going to be very small. That means the top, the numerator, is going to be very small. That's going to make this close to 0.
And also you can see it graphically, because the point that's closest to A is closest to 0.
Right, exactly. Go ahead.
Can you like plug in a fake number and run the math?
Yeah, sure. Yep. All right.
Because before you even do the numbers, I don't understand the numbers yet. I see from the graph. If you shrink B area towards A, then it goes back to this 45 perfect line thing. And this straight line for me is the perfect equality.
Uh-huh.
Whenever you have the curve, it's an equality. The more, okay,
It's the visual
the more this
representation.
thing, the more the increases towards here, the bigger this is, the bigger is inequality. The more it moves back to the straight, it reduces inequality, so it's perfect equality.
Exactly.
From the numbers, I see that.
Okay. Well, I'll try and give you an example here to make it a little bit more clear numerically. All right. Let's start with what A plus B is. A plus B is this entire area here. How do I figure out the size of that area?
It's like a triangle. This one side.
Okay.
How do you, well, you have to now name them A, B, C, whatever, and then it will be 2 times A plus B.
It's not
I
that.
have to remember.
You're close. The
Yeah.
formula for a triangle is 1/2 the base of the
Yes.
triangle times the height of the triangle.
Yeah.
In this case, my base is 100,
Mhm.
my height is 100. So it's 1/2 100 times 100 should be 5,000. I did my math right there.
We're just solving the area, the whole area A and B.
The whole area A and B. All right. So right now, this is 5,000. Now, I'm going to swag this here. All right.
Presumably, if we had this in a problem set, we would be given the value of A, right?
Yes, that's why I was saying I don't want you to get bogged down in the numbers. I just want you to understand where it comes from.
Got it.
All right. So if this curve swung out in such a way to occupy half the area of this triangle, then it would be 2,500, and your Gini coefficient would be 0.5.
Can you please repeat the 2500 part again?
Sure. I said if this area took up half of this triangle, I already know the triangle has an area of 5,000, so A has 2,500. Now to go to the extremes, if I have perfect equality, then this line is the distribution. So the area A is 0. It's tiny, all right? So my Gini coefficient under that condition would be 0 divided by 5,000, which is 0.
It's in no circumstances A equal to B. In that, I thought that when it's
No, it could be.
perfect equality, then you will have A equal to B.
No,
No.
no.
I think
When it's perfect equality, A is 0.
Okay.
All right?
That is perfect equality. What you-
Yes.
Yeah.
Yep.
Meaning B doesn't exist.
A doesn't
A
exist.
doesn't exist.
B would be this entire area here in
Because
perfect equality.
Because A and B are spatial, they're not the line. It's not,
Yeah,
we're not
but I
measuring the
see.
line, we're measuring the
You
space.
just
Is that right?
Yes.
You just mentioned in the perfect equality, A would equal 0.
Right. So
Yeah,
B
then
would be
it's
huge.
non-existent.
So the top is 0. All right, got it? All right. Now, if we have horrendous inequality, then huge portions of the population would earn very little. And then the oligarchs or the monarchy or whoever, they have everything. So A is enormous and B is almost nothing. All right? So if B is effectively 0, then I have A over A plus 0, which is the same as 1. So that's why if you've got inequality, your Gini coefficient is close to 1. If you've got equality, it's close to 0. Thank you. Sure. Sure.
Okay, so for the perfect equality portion of this,
Mhm.
A is 0. Can you say that one more time? Why is this? I understand it spatially now. I think
Okay.
better than I understand. Like, why is it 0? I see 0 at point 0, 0 on the axis.
Okay.
Right?
Yeah, just remind me again, which situation are you asking about?
Perfect equality.
Perfect
Why
equality.
is A 0?
Okay. Because A is the area between the 45-degree line and
And
the
the
actual Lorenz curve. All right? So,
Which
if
is 0. Okay, and the danger is you look at the line and you think it's going to be 1 over 1. It's not 1. It's 0 because it's the area.
it's
And
the
there
area
is no-
between.
There is no
Yes.
space between. Okay.
Exactly.
Then why are you showing B as 0 there?
Because this was perfect inequality.
Ah, this is equal, sorry. And this is equal, actually.
All right. Now, the last thing I want to go over is the poverty gap.
Good. Sorry.
Yeah, sure.
So, if it's 0.5, what
Yep.
does it tell you about? If Gini
Oh, yeah.
coefficient is 0.5, I'm thinking of the hypothetical question on exam.
Sure.
What does it tell me in terms of?
The number by itself doesn't tell you very much. What it's used for is comparison. All right. So just to give you an example from the book here. All right. The Gini coefficient of Ethiopia is 0.3, and the Gini coefficient of South Africa is 0.57. So Ethiopia 0.3.
So can I conclude that inequality is high in Ethiopia? South Africa?
Talk me through it.
Well, I just understood that the lower the Gini coefficient number, the
Higher equality.
higher is the inequality.
No, the
Equality.
I'm sorry. Can you please repeat?
Sure. Equality. Let's go. Let's write it here. We've got
The higher the number.
from
the higher-
perfect equality perfect inequality. From 0 to 1, perfect equality to perfect inequality. All right. So an example test question would be, here are two countries, two Gini coefficients. What does that mean, and why is it intuitive? So talk me through that.
Now I can say, perfect inequality is 1. It means that it's South Africa.
Go, but someone explain to me what we've got here.
Which one is which more?
What does this mean,
Okay.
and why is that intuitive?
For me, I think the easy way for me to remember is the higher the number, the higher the inequality.
Okay,
Because the
great.
higher the number, the closer you get to 1, the more you're trending towards a perfectly unequal society.
Great. So give me which one is more unequal, and why is that intuitive?
South Africa has a higher inequality than Ethiopia. Why is that intuitive? You mean with regard to those particular countries themselves? Probably because because South Africa is a more highly developed nation, and therefore there's a greater disparity among incomes. Ethiopia, being a less developed or an underdeveloped nation, might have a greater might have a closer proximity towards equality of incomes, but probably they're generally very low.
Okay, that's a good answer. All right. The way I would shape it is, there's more income equality in Ethiopia than South Africa. The reason that's intuitive to me is everyone's poor in Ethiopia, so the income distribution tends to be more equal. South Africa went through years of apartheid, so you've got a lot of wealth consolidated in a minority white population that is not spread equally across the total population of the country. All right. Now, I'm not saying that's the right answer, but that's the way I would shape a text question around the Gini coefficient.
Okay.
All right. All right, the last piece is the poverty gap. Think of the poverty gap as, it's not something necessarily poverty gap is more useful on an individual country basis. And there's a formula for it, and I'll break down what the formula means. Okay, this stuff looks complicated. It's not that complicated. I'm going to put one graph up here. It's out of the book to help illustrate why this is significant. And you need to think of poverty gap as the severity of poverty. How much income it would take to move the people who are in poverty above the poverty line.
Again, how much, what would take?
Think about how much money it would take to get everyone who's below poverty above poverty in a given country.
Thank you.
Sure. This graph is from page 211 if you wanted to reference it yourself. Here's why it's useful. Consumption per capita. How much each person is spending on average per day. So for our purposes, generally, we're looking at consumption below $1 a day is considered abject poverty. The y-axis is the percent of the population in that situation. So you can see that this portion of the population is below the poverty line. Now, without looking at any numbers, if I take two situations where you, let's say that this shaded area represents 10% of the population. So 10% of the population is below the poverty line in this country, and that graph is for Bangladesh. Let's say this is another country and they've also got 10% below the poverty line. What you need to notice is, see how the bulk of this is right against the dashed line, which is the poverty line? Whereas this one, it's not. It's further to the left. What that means is that this population, this 10% under the poverty line, they're subsisting closer to maybe 30 cents a day, and the average here is maybe 60 cents a day. Right? It's going to be a lot easier to get this country's 10% above the poverty line than this one, because they're further away from it. Does that make sense? So that's it graphically, and that's what the poverty gap concept is helping us figure out. How much money is it going to take to get the average person above the poverty line? So when we go to this formula here, we're saying this concept of the poverty gap is equal to the poverty line, which in our case is $1. Now let's take Bangladesh and say that the meat consumption for their population is 60 cents a day. Now, the Headcount Index we already talked about is the number of people below the poverty line over the total population. So I said, let's call that 10%. Let's say it's 10% of the population. Does everyone see how I use the numbers we talked about with this formula and put them in here?
Would you take 60 or 0.6?
It says 0.6.
Oh.
Sorry. 0.6 right there.
Headcount index, because it's index, obviously, it's always a percentage, right?
Correct.
You mentioned that, maybe I missed it.
Yep. It's right here. So it's the total number of people below the poverty line over the total population.
Can I ask a question? Please?
Sure.
The 60% cents would be on which of the graphs?
Okay, right here.
And
So what
this
I'm
is-
saying is the average of all these, let's say, is somewhere here. And I'm saying that's 0.6. And then I'm saying in this country, the average of this 10% is right here. We're going to call that 0.3.
This is, you're comparing a country to another one, or is this?
Yeah, this is a made-up country. We're going to call this super poor country. And super poor country is even more poor than Bangladesh.
And this one is obviously, oh, I see.
So the poverty gap turns out to be 0.4 over 1 times 0.1, 0.04. So that's for Bangladesh. The poverty gap for the super poor country is equal to $1 minus 0.3 over 1. It's also 10% of their population. So that ends up being 0.7 over 1 times 0.1, 0.07. So you can see that for poverty gap purposes, higher is worse. It's going to take more effort the higher the poverty gap number is.
Your property gap. Oh, no. I was gonna say you can never be above 0.1, but that's because we're using the Headcount Index of 10%.
Yeah, you can't, let's see.
You can never,
Yeah.
What does it
your
point-
number can never be higher than your Headcount Index.
Correct. That's correct, right? Because the number, the mean consumption has to be below your poverty line. Otherwise, those people wouldn't be below the poverty.
What does it mean, 0.07? Does that mean,
How would I want to catch that?
is it because you said you said
You
how
want to
much
think about
income?
it as the severity of poverty.
Because you said how much income
Yeah.
does it need to shift the population above the poverty line? So the 0.07 is that dollars, percentage, something?
I totally understand your question, and I'm failing on a good way to explain it.
Because if that's how much it is that we need, if this is the indication of the income that we need in order to move them from the